I thought there was nothing I could do about it. But I was wrong. There is room for improvement. SDR receivers are versatile and relatively inexpensive compared to conventional ones. You can find links to some models below. Unfortunately, their weakness is in interference resilience. They are connecting to a computer via USB, which can lead to noise. And they are also sensitive to intermodulation unless high-quality preselection filters are used. In a previous video, we demonstrated significant improvements on higher shortwave bands using ferrite blocks. However, we weren't able to completely eliminate the interference at lower frequencies. At first, I thought it was in-band interference, as my indoor antenna certainly picks up a lot of interference from electrical devices in the house. But wait a minute. Is my conclusion correct? Perhaps some of the interference is caused by mixed signals from out-of-band interferers. In this context, we were demonstrating improvements with frequency-selective lambda loops for 868 MHz and 435 MHz. However, the lambda loop would be far too large for long-wave frequencies, as the wavelength is several kilometers. For my SDR receiver, I would like an antenna that can be placed in a room or on the balcony. So, today we are investigating 3 small electrical loops that are suitable for this purpose. My test setup consists of 2 2-meter long coaxial cables and a homemade 1-to-1 balloon. The somewhat unusual design with the screw terminals allows me to set up different loop antennas using cable bridges. For the simple loop, I'm using the outer conductor of the coaxial cable, meaning the effective currents are flowing only on the outside. In the next step, we are creating a so-called shielded loop using the inner conductor as an antenna. It's practically the same principle as a magnetic field sensor. The outer conductor of the coax cable shields interfering electric fields. The outer conductor must remain open at the top to allow the RF energy to flow. I will reveal some secrets to this in a separate video on Electronics Unmasked. It might be worth subscribing to the channel. With this wiring, we are getting a so-called Möbius antenna. The inner conductor on one side is connected to the outer conductor on the other side. This creates 2 turns, so the antenna theoretically delivers twice the voltage. Here's a tip for everyone who enjoys developing own electronics. PCBWay, the sponsor of this video, offers great deals on PCBs and custom manufacturing. It's amazing what they can do for you at fair prices. We've not only had PCBs made for classic electronic boards, but also casing parts and high-quality antennas. Take the easy way with PCBWay. The balloon has 3 parallel windings with 8 turns each. For the simple loop, we only need 2 of them. The third winding is for grounding the shielded and the Möbius loop. I will experiment with the wiring, as I'm not quite sure which is best yet. Radiation patterns of an electrically small loop and a small dipole are pretty similar. Ensuring the appropriate alignment, a fair comparison between the dipole and the loops should be possible. An RSPDX from SDR Play is very useful, as it allows switching between 3 antenna inputs. My dipole antenna is connected to input A and the various loops to input B. In my room, the antennas are aligned so that their radiation characteristics point in the same direction. One antenna is producing less noise than the other. This statement is misleading, at least with the passive antennas used here. First, we have the inherent noise of the receiver or preamplifier. We were previously explaining how to calculate it from the frequency bandwidth, temperature and the Boltzmann constant. The antenna won't change this. Second, we have natural noise from space, which has been measured, so it can be estimated for all frequency ranges. It could be reduced by a narrow directional antenna characteristic. Third, we have man-made noise, which, as we have seen, is becoming more and more of a problem. Actually, in my case, I can only do something about this kind of noise. Man-made RF interference can be strong sometimes. I'm curious to see if my suspicion about intermodulation is correct. I'm currently receiving the frequency band from 0 to 500 kHz using a wire dipole. The strength of the DCF77 time signal is approximately -117 dBm. The signal-to-noise ratio is approximately 11 dB. In the band, we can see these interference peaks. But look what happens when I switch to the simple loop antenna. The interference peaks are completely disappearing and the time signal has become stronger. It's now -109 dBm with a significantly improved SNR of 19 dB. We are even seeing signals that we couldn't receive before. Cool, isn't it? Now I'm switching to the shielded loop. The signal strength remains the same, but the SNR improves by 1 to 2 dB compared to the simple loop. The Möbius loop is delivering the strongest signal of -105 dBm, achieving an SNR of about 25 dB. For the comparison, I chose the DCF77 time signal because it reaches me with a relatively constant field strength. At the frequency of 77.5 kHz, the loop antennas have significant advantages over the dipole antenna. With the shielded loop, the SNR can be slightly improved compared to the simple loop. The Möbius loop increases the signal strength by another 4 dB. Theoretically, doubling the voltage is corresponding to 6 dB. Surprisingly, the SNR improved by 4 dB over the shielded loop. The measurement results are actually confirming what you would expect from the theory. We will now going through all broadcast bands in the same order. On long and medium wave there's not much going on. Reception is less noisy with the loops. On the lower shortwave bands the noise floor is reduced, but we can't eliminate the peaks even with the shielded loop. Reception of radio stations is much better though. On mid-shortwave bands, the peaks can be completely eliminated with the loops, thus achieving crystal clear reception. At higher frequencies, the signal from the loops becomes weaker, and in terms of interference there seems to be no advantage over the dipole. Loops are significantly improving the reception with my SDR receiver in the lower frequency ranges. The noise floor is lowered, interference peaks are removed, and the signal strength is improved. On mid-range shortwave, they are reducing interference, making signals better audible compared to the dipole. However, they cannot completely eliminate the noise peaks. On higher shortwave frequencies, the loop's signal strength is lower than from the dipole, which makes their use less attractive. The different loops and the dipole antenna all have their uses. Depending on the frequency range and type of interference, one or the other delivers better results. Maybe it would be worthwhile to build loops in different size to better adapt to the frequency bands. As I reported earlier, starting with my SDR receiver was rather disappointing on long and shortwave. But with the measures shown, I now have crystal clear reception on some bands. There's one more thing I'd like to mention. Grounding the loop via the third winding of the balloon improved noise reduction in all my experiments. If only I paid more attention to my own videos about intermodulation, I would have solved the problem earlier. Next, I'd like to create a solid loop made of high quality material. By the way, there are inexpensive loop antennas available for purchase. You will find the links below. Many thanks to my viewers whose feedback sparked the idea for this video. Someone just commented, "Your USB power supply could be a root cause of interference." Oh yes. We will investigate that soon. Maybe we will get the lower shortwave bands clean as well. So, folks, drop your comments below. Now, stay tuned and don't forget to support the channel. See you soon in the coming episodes.